Download this code from codegive.com, link in the description below. Linux kernel 6.1 LTS, what you need to know, with code examples. The Linux kernel 6.1 long-term support, LTS, version is a significant milestone representing stability and long-term maintainability. This tutorial dives deep into kernel 6.1 LTS, exploring its key features, improvements, and impact, and providing practical code examples where applicable. This guide is designed for system administrators, developers, and anyone interested in understanding the inner workings of Linux. 1. What is an LTS kernel? LTS, long-term support, kernels are specifically designated versions that receive extended maintenance and bug fixes for a longer period than standard kernels. This makes them ideal for enterprise environments, embedded systems, and any situation where stability and predictable updates are paramount. Extended support typically, an LTS kernel receives support for approximately 2 to 6 years, whereas a non-LTS kernel is usually supported for only a few months. The exact duration is decided by the kernel maintainers. Stability focus LTS releases prioritize bug fixes and security patches over new features. This ensures a more stable and reliable operating environment. Predictability updates are released at predictable intervals, allowing administrators to plan and test upgrades effectively. Target audience enterprise servers, embedded systems, industrial applications, and long life cycle products. 2. Why choose kernel 6.1 LTS? Kernel 6.1 LTS offers a compelling blend of features and stability. It's a solid upgrade path from older kernels if you are prioritizing long-term maintenance and a well-tested code base. Here's a summary. Long-term support provides extended security and bug fixes until approximately December 2026. Always confirm the specific end-of-life date with the kernel maintainers as it can change. Performance improvements includes numerous optimizations and performance enhancements, impacting areas like file system operations, networking, and CPU scheduling. Hardware support supports a wide range of new hardware, ensuring compatibility with the latest devices and peripherals. Security enhancements addresses various security vulnerabilities, providing a more secure operating environment. New features while focused on stability, LTS kernels still incorporate significant feature additions that have been well tested in prior mainline releases. 3. Key features and improvements in kernel 6.1 LTS. Kernel 6.1 LTS includes a plethora of improvements and features. Let's explore some of the most notable ones. 3.1 Rust support, initial infrastructure. This is arguably the most groundbreaking addition. Kernel 6.1 marks the initial infrastructure for incorporating Rust code into the kernel. While not a full-fledged replacement for C, Rust provides memory safety guarantees and helps mitigate common vulnerabilities associated with C development. Motivation improved security, reduced risk of memory corruption bugs, buffer overflows, use after free, etc. Rust's ownership and borrowing system enforces memory safety at compile time. Current state the Rust infrastructure is primarily for developing device drivers and modules. The core kernel remains written in C. Future the intention is to gradually integrate Rust into more parts of the kernel over time, but C will remain the dominant language for a long time to come. Example, simple Rust kernel module. Explanation no_std, indicates that this module doesn't link against the standard Rust library, which relies on an operating system. Kernel modules run in a bare metal environment. Extern crate alloc imports the alloc crate, providing memory allocation functionalities, like string, vec. Use rust kernel Linux util : uses a crate that provides helpful utilities like logging and mutexes designed for a Linux kernel environment. Global allocator specifies a global memory allocator. In this case, it uses linked list allocator locked heap. Panic handler defines a panic handler, which is called when the Rust code encounters an unrecoverable error, panic. This prevents a kernel crash by logging the error. No mangle pub extern cfn start, this is the entry point for the kernel module. It's marked no mangle to prevent the Rust compiler from renaming the function, and extern c ensures it uses the c calling convention. Log info uses the log crate to write information messages to the kernel log, viewable with dmesc. *kdb test. This is a hypothetical KDB, kernel debugger, interface. The test string would be used in the kernel debugger to call the code inside the curly braces. Important * developing Rust kernel modules requires the Rust compiler, cargo build system, and specific crates designed for the kernel environment, like the Rust kernel Linux util crate. You'll also need a way to load and unload the module, often using insmod and rmod after compilation. Building and loading, example. 1. Install Rust and cargo *. Follow the instructions on the Rust website, https://www.rustlang.org/ https://www.rust-lang.org. 2. Install dependencies *. 3. Create a cargo.toml file *. This describes the project and its dependencies. 4. Build the module *. 5. Compile the Rust module *. You'll need to cross-compile for the kernel architecture and link it correctly. The specific commands for this can be quite involved and depend on your target system. You will likely need to create a build.rs file to set the appropriate compiler flags. Example. Note *. This is a basic example. Creating a fully functional and safe Rust kernel module requires deep understanding of both Rust and the Linux kernel. Cross-compilation, memory management, and handling kernel-specific data structures are crucial aspects. Refer to the official Rust for Linux documentation and examples for more detailed guidance. The example above assumes that you also have a library for kernel debugging that needs to be linked to it. 6. Load the module, as root. 7. Check the kernel log *. 3.2 Multi-gen LRU, mglru. Mglru is a significant improvement to the kernel's page replacement algorithm. It helps the system make better decisions about which pages to evict from memory when memory pressure is high. Motivation * improved performance, especially in memory-constrained environments and under heavy workloads. How it works * mglru tracks the age and access patterns of pages across multiple generations or levels of LRU lists. This provides a more nuanced view of page activity compared to the traditional single-list LRU, leading to more efficient page eviction. Benefits * reduced page faults, lower I/O, and improved responsiveness under memory pressure. Better overall memory management, especially for workloads with varying memory access patterns. 3.3 BPF, eBPF, enhancements *. Kernel 6.1 includes many enhancements to the extended Berkeley packet filter, eBPF, subsystem. eBPF allows you to run sandboxed programs within the kernel without modifying the kernel source code. Asterisk motivation asterisk increased flexibility, programmability, and security for kernel-level monitoring, tracing, and networking. Asterisk key improvements asterisk. Asterisk new BPF helpers asterisk functions that BPF programs can call to interact with the kernel. Asterisk improved JIT compilers asterisk better performance of BPF programs. Asterisk enhanced security asterisk more robust verification and sandboxing mechanisms. Asterisk use cases asterisk network packet filtering, performance analysis, security monitoring, system call tracing, and more. Asterisk example, simple BPF program in C. This program traces the open system call and prints the file name being opened. Explanation asterisk. Asterisk include linux/config.h and linux/trace.h, includes necessary kernel headers. Asterisk struct data_t, defines a structure to store the data we want to collect, PID, command name, and file name. Asterisk BPF_perf_output, events, defines a perf event output map named events that will be used to send data from the BPF program to user space. Asterisk int trace_entry, struct pt_regs *ctx, const char asterisk file name. This is the function that will be executed when the open system call is traced. It receives the registers, ctx, and the file name as arguments. Asterisk BPF_get_current_PID_t gets the current process ID, PID. Asterisk BPF_get_current_com gets the command name of the current process. Asterisk BPF_probe_read_str reads the file name from kernel memory into the data.file name buffer. This is necessary because BPF programs cannot directly access kernel memory. Asterisk events.perf_submit, ctx, and data, size of, data, submits the collected data to the events map. Compiling and running asterisk. You'll need the BCC, BPF compiler collection, tools installed to compile and run BPF programs. 1. Install BCC asterisk. The installation process varies depending on your distribution. Refer to the BCC documentation, https://github.com/iAdvisor/bcc, https://github.com/iOvisor/bcc. 2. Compile the BPF program asterisk. 3. Create a Python script to load and run the BPF program asterisk. 4. Run the script, as root. This script will trace the open system call and print information about the process, PID, and the file name being opened to the console. Important asterisk. BPF programming requires a good understanding of kernel internals, memory safety, and system call conventions. It's crucial to test BPF programs thoroughly in a safe environment before deploying them to production systems. Always be cautious when working with BPF, as incorrect programs can potentially cause kernel instability. 3.4 Zoned Namespace Block, ZNS, Device Support asterisk. ZNS is a new type of storage device that exposes zones to the host. This allows the host to have more control over how data is placed on the device, leading to improved performance and efficiency. Asterisk motivation asterisk. Improved performance, reduced write amplification, and better utilization of storage capacity, particularly for large-scale data centers and storage systems. Asterisk. How it works asterisk. ZNS divides the storage device into zones, each with a specific capacity. The host is responsible for managing these zones, writing sequentially within each zone, and resetting zones when they are no longer needed. Asterisk. Benefits asterisk. Asterisk. Lower write amplification asterisk. By writing sequentially within zones, ZNS reduces the need for the device to perform garbage collection, which reduces write amplification and extends the lifespan of the storage device. Improved performance sequential writes and reduced garbage collection result in faster write speeds and lower latency. Better capacity utilization ZNS allows for more efficient use of storage capacity by eliminating the need for over-provisioning. Kernel 6.1 support Kernel 6.1 provides the necessary drivers and infrastructure to support ZNS devices. This allows file systems and applications to take advantage of the benefits of ZNS. 3.5 RISC-V improvements Kernel 6.1 brings further improvements and enhancements to the RISC-V architecture. RISC-V is an open-source instruction set architecture, ISA, gaining popularity in various domains, from embedded systems to high-performance computing. Motivation to improve the usability, performance, and support for RISC-V based systems. Key improvements support for new RISC-V extensions support for new instructions and features specific to RISC-V processors. Performance optimizations various optimizations to improve the performance of RISC-V systems. Improved hardware support better support for a wider range of RISC-V hardware platforms. Examples Important the code samples provided in the RISC-V section are for demonstration only. Working with RISC-V assembly requires thorough knowledge of the RISC-V ISA. The compilation and execution of RISC-V assembly code need a compatible tool chain. 3.6 Performance Monitoring Subsystem, PMS, Core The PMS core is an addition to the Linux kernel that adds several hardware-independent PMU, performance monitoring unit, to the kernel that allows to enable event counters with programmable counter resources. Motivation provide abstraction layers for PMU and improve perf trace performance. Key improvements hardware-independent PMU abstract PMU resources and provide interfaces for perf trace. Performance optimizations use hardware-independent PMU events to record core samples for performance monitoring. Improved hardware support better PMU resource management, allowing better support for performance monitoring. 4. Upgrading to kernel 6.1 LTS. The process of upgrading to kernel 6.1 LTS depends on your Linux distribution. Here's a general outline. Check distribution support determine if your distribution provides pre-built kernel 6.1 LTS packages. Using pre-built packages is the easiest and safest option. Distribution specific tools use your distribution's package manager, example apt on Debian/Ubuntu, yum on CentOS/RHEL, Pacman on Arch Linux, to install the new kernel. Follow your distribution's instructions for kernel upgrades. Build from source, advanced if your distribution doesn't provide pre-built packages, you can build kernel 6.1 LTS from source. This is a more complex process that requires compiling the kernel, installing modules, and configuring the bootloader. Download the source code download the kernel 6.1 LTS source code from https://www.kernel.org/ https://www.kernel.org configuration use make menu config or makes config to configure the kernel. You can start with your current kernel's configuration file to ensure compatibility. Compilation use make to compile the kernel. Installation use make modules _install and make install to install the modules and the kernel image. Bootloader configuration update your bootloader, example grub, to boot from the new kernel. 5. Important considerations before upgrading. Backup. Always back up your system before performing a kernel upgrade. This will allow you to restore your system to its previous state if something goes wrong. Hardware compatibility. Check if your hardware is fully supported by kernel 6.1 LTS. Review the release notes and consult with hardware vendors if necessary. Driver compatibility. Ensure that all necessary drivers, example graphics drivers, network drivers, are compatible with kernel 6.1 LTS. You may need to update drivers after the upgrade. Testing. Thoroughly test the new kernel in a non-production environment before deploying it to production systems. This will help you identify any potential issues and address them before they impact your users. 6. Conclusion. Kernel 6.1 LTS is a significant release that offers a compelling combination of stability, performance enhancements, and new features. It's a solid choice for systems where long-term support and reliability are paramount. Understanding its key features, particularly Rust support, GLRU, and BPF enhancements, is crucial for taking full advantage of its capabilities. Remember to thoroughly test and plan your upgrade process to ensure a smooth transition. By carefully considering the information in this guide, you can confidently leverage the benefits of kernel 6.1 LTS for your systems. Disclaimer: kernel development is a complex and rapidly evolving field. Always refer to the official kernel documentation and community resources for the most up-to-date information. This guide provides a general overview and should not be considered a substitute for expert advice. Remember to consult kernel documentation and test thoroughly before deploying any kernel changes to production systems.